All right, we are recording now. Let me make sure nobody else has tried to get in. No, they haven't. Um, the there was a question about where the second test was posted, so I went into Blackboard, and it's under Messages, which is under this envelope icon here. That means Messages, and under this course, Messages, and then there's test 2. Test 1's there. Now to open it, I don't know, you probably know this from the last time, you have to click on the 3 dots here to get it to upload, and then when it uploads it'll come down, or download, I can't remember which direction it's going. When it finishes counting off how much it's still got to do, then it'll show up down here in the corner, and that's when you click on it. You can open it and print it from there or whatever. All right, so that was a question there. I think I will get out of Blackboard then, because I don't think we need to be here any longer. And screen sharing stopped, so let me go back and pick up screen share again from where we were, and that's here. Okay, now I've got to move my taskbars again. This is such a sort of a pain. Okay, and there's still just the 2 of us, so I guess can't think of any other. Do you have any other questions, issues, concerns? Okay, now you got very faint there. I don't know if it's my hearing or your. Wait, one thing I haven't done well is need to clip this on my. Okay. All right, so I guess we'll get started with where we left off last time. We're beginning in chapter 4. Pretty nice shot here. It was a shuttle launch. I never got to see one, but my father-in-law worked for NASA, and he got to go down and see one that was carrying up an experiment he had helped to develop. So he got to see that launch. He said it was pretty impressive. So anyway, enough of that. Let's go on to 4. As I think I mentioned before, chapter 4 has 10 sections. I don't think we're going to get through 10 sections. We're going to do this preliminary theory, which usually is a bunch of stuff at the very beginning, which you kind of need, but it's just blah, blah, blah-ish, okay? And then reduction of order, we will need that concept later on. And then we'll get into homogeneous linear equations with constant coefficients. Now these are all higher order equations. Then we'll go into undetermined coefficients, and we'll do the superposition approach. The book says do either 4-4 or 4-5 depending. I've taught them both, and students seem to like the superposition approach better. It seems, to me, it's more consistent with everything we've done before. Annihilator is not that much different, but it just seems like it goes over. So we'll skip 4-5 and go to 4-6, and then keep going as far as we can till we run out of term, is what I'm guessing, because they have shortened the summer term. We're now ending sometime, is it about the 3rd week in July, and we're now already in July, and so they've really, and there is a legitimate reason for it. I wish they had planned better and had classes being a little bit longer if they were going to do this, but they didn't. But we are changing our entire administrative package. The 2-year college system is mandated. All the 2-year colleges have to be on the same system. They've determined what system it is, so we're going from what we were on, which is an ancient system which needed to be changed. It was called the Alliance system, and they're going to the system they call Banner. And so that's happening, and everything has to shut down in Alliant by the end of July, and everything has to be in Banner by the 1st of August. And they're already working on it, but we can't do, and since the course was set up in Alliant, we have to end it before Alliant dies. for us, and literally it will. It will be removed. We might be able to extract some things from archives, but that's it. We won't be able to do anything what I would consider active anymore. So that's why they moved up the end date of the end of the term to give everybody a chance to get all the grades in and everything in before the whole system dies. So sorry about that. But there is a good news, bad news situation coming up. Are you aware of it? We've gone to a 4-day work week, Monday through Thursday. So our Fridays are off anyway. Well, the 4th of July is on a Saturday. So everybody else who's on a 5-day work week, they have their holiday on Friday, the 3rd of July. Okay? But we already have Friday off. So rather than doing the smart thing, in my mind, the correct thing, the thing that makes the most sense, we should have had today off but no, they decided to give Monday off. Okay, so in our system, or at least at our college, Monday is our holiday, not today. Sorry about that. And I really am, because if you also see some of the dumb choices we've made, they decided, and I've begged them repeatedly, do not ever start a term on a Tuesday or a Thursday. Always start a term on a Monday or a Wednesday. And I've explained it to them. But they're administrators and they don't listen. They don't take suggestions very well. They do whatever they want to. And here's why I say that. Every term, fall, spring, and summer, within the first week or two of class, you lose a Monday. Labor Day in the fall, Martin Luther King Day in the spring, and Memorial Day in the summer. The summer is a prime example of that. Completely ignoring the request, they started on a Thursday. So we had classes on Thursday. The next Monday was Memorial Day. Then we had classes on Tuesday. 2 classes for Tuesday, Thursday, 0 classes for Monday, Wednesday. Okay? First Monday, Wednesday class was after a week's of material had already been happening. It's already a shortened term. Okay, so after a whole week, the Monday, Wednesday classes are 1 week behind before they ever started. Okay, so they had an opportunity, a perfect opportunity to make up one of those days by having the holiday on Thursday, today, rather than Monday. What did they choose? Let's have the holiday on Monday. And I begged them when I saw they did that. I said, please consider changing this. And I went through the whole litany of why, and still not a single. They didn't even bother to respond. Okay, so the bad news is Monday is a holiday. The good news is it doesn't affect us any because we have Tuesday, Thursday classes. So here we go. All right. And that's why I was saying we may not finish everything in this chapter. We'll do our best, but I don't think we'll get there. So let's scroll on down. Sorry, that was too much of a gripe. Okay. Now, let me move us out of the way as much as I can here. Okay. So we've turned from chapter 2, where we were doing first order differential equations only, and all those techniques, separation of variables, linear, exact, homogeneous. Yeah. Now we're going to talk about homogeneous in a different form there, as you just saw. And this is going to be so hard to do. I've moved this right into the way of the upper arrow. So okay. As you saw here, there's homogeneous linear equations with constant coefficients. That's not the same homogeneous we were doing before, which meant every term had the coefficients had the same power, okay, or degree. Different homogeneous here. Same term, different meaning, okay? So did want to point that out. So those other techniques, Bernoulli, all those things, really none of them going to work. Maybe some of the approaches will be similar, but those techniques were for first order, pretty much first order only. Okay, so that's why it says here we now turn our attention to ordinary differential equations of order 2 or higher. Okay, and the first 7 sections we examine the underlying theory and some solution methods. I'm going to try to get through the theory as quickly as possible. The drags, and then we'll conclude with a brief examination of solution methods for nonlinear. That's where you get into Green's theorem and some of these other things, which I don't know if we're going to get to, and I can't even remember if they're in the course description. I've got to go back and check that. So here's the preliminary theory, which is usually sort of a drag. Chapter 2, we did first order equations. I've got my thing in the way here, so I'm going to move us up to the very top. Okay, now we're more out of the way. Okay, nope, mess that one up. Okay, now I'm going to try to move a little bit this way. Okay, yeah, now we got it. You can't see what I'm doing, but it's my block that gets in the way here. So we looked at that, able to solve a few first order differential equations, we're recognizing them as either separable, linear, exact, having homogeneous coefficients. See, that's a different thing from homogeneous equations. Having homogeneous coefficients, that means all in the same order. And then we did some substitutions and things like this. Even though the solutions obtained were in the form of a one-parameter family, that family, with one exception, did not represent the general solution of a differential equation. Now, what do we mean by general solution? Family of solutions defined on some interval I that contains all the solutions of differential equations that are defined on that I. Only in the case of linear first order differential equations were we able to obtain general solutions by paying close attention to the continuity conditions imposed by the coefficients of the equations. Now, I tried to point out things to watch for, and so we sort of did a good job of talking around it, but only linear you were guaranteed. So because of the primary goal of the chapter is to find general solutions for linear higher order differential equations, let's see what we mean by going back to the basic theory of linear equations. Okay, now the term linear has the same meaning. Remember, that was from the very beginning. You cannot have a y and a y prime in the same term. You can't have a y squared in the same term. You can't have a y double prime squared or cubed in the same term. You can't have a y to the 1/2 power in the same term. You can't have a sine of y or any other function of y. Y's and the derivatives of y's have to show up only in the power of 1. Okay? That's one way to express it. So here's what we mean. Here's what we're trying to do, an nth order initial value problem. Okay, it has some coefficient. Notice it's only a coefficient of x's. Then you have the nth derivative of y with respect to x plus some other coefficient that only has x's in it times the next lowest derivative of y with respect to x, plus keep on going down and down and down till you finally get to a sub 3 of x, y triple prime, dy d3 prime, a sub 2 of x, and again they're only coefficients of functions of x's, times the second derivative of y with respect to x plus a sub 1 of x, dy dx, plus a sub 0 of x times y. And then over on the right you have some function of x. Again, all your coefficient functions and the g at the end are only coefficients of x. You have no y's to any other power, no derivatives of y to any other power other than 1. You can't have a fractional power, you can't have a negative power, you can't have a multiple power, okay? No other power except power of 1. All the derivatives and all the y's, and you can't have 2 of those in the same term, okay? Any derivative is that's the only expression of y in that term, okay? And y itself. And y cannot be a function of anything else. In other words, you can't have a sine of y, e to the y, anything else. X is to your heart's content, okay? Any functions of x in the coefficient functions are over here. I'm not saying you'll be able to solve them, but you can have them and still be a linear equation. Now, that's the equation part, the differential equation part. Here are the initial conditions. Now, with this first order, you only had one initial condition, as in y of x0 is equal to y0. But if you have an nth order, that means you have n initial conditions. Now, if you first glance of this, it looks like it only goes to n minus 1 until you realize that you started counting at y0, okay? y0, first derivative, second derivative, third derivative. See, you're always, the number of derivative is 1 behind how many conditions you have, okay? So you do have n conditions. They only go up through the n minus first derivative, okay? Now, one other little thing I didn't say, this a sub n here cannot be 0. That could be a constant, it could be anything except 0. All the rest of these can be anything, all the a's. They can be any function of x, including 0. But the reason this one can't be 0 is that would make your whole term 0, and then this wouldn't be an nth order differential equation. It would be an n minus first or something lower, okay? So the a sub 0 of x cannot be 0, okay? I needed to say that, left that out before. So here are your initial conditions. Notice they're at the same values of x always. Okay? If they're at different values of x, we call them boundary conditions. These have to be initial conditions at the same values for x. Your function value, your first derivative value, second derivative value, all the derivatives up to the n minus first derivative at the same value. All right, that was a quick, maybe not quick enough, rephrase of what we mean by an nth order initial value problem. Linear nth order initial value problem. Okay, now here they're talking about all this stuff again, and they just use the same phrase here, but these are constants. This is your function evaluated at a constant, and there's the constant that function is evaluated at. So we're always at x0, but only y0, of course, would be the one for the 0th derivative, okay? After that, the first derivative constant is called y1, the second derivative is constant y2, and all like that. When you get into real to the numbers there rather than the letters, it doesn't really matter. It's really easy to see, okay? Now, but just a little nomenclature there. Okay. Now, existence and uniqueness. When we're talking about things like this, solutions. Back in section 1.2, I don't remember that far back, but anyway, somewhere back there, we stated a theorem that gave conditions under which the existence and uniqueness of a solution of a first order initial value problem was guaranteed. The theorem that follows, it gives sufficient conditions for the existence of a unique solution to this one. That was before first order, this is multi-order. So your a sub n of x, a sub n minus 1 of x, all the way down to a sub 0 of x, and the g of x, every one of those has to be continuous on the interval of integration, the I, okay? And what I said before, the a sub n of x, that first one cannot be 0. If it were 0, you don't have an nth order equation. you have an n minus first or something less. So to make this an nth order, it has to be non-zero. For every x in the interval, and that's the one I tried to point out to you in all the things, if that a sub n could be a 0 anywhere, that may throw a what was the term they used for those solutions? I want to say specific, that's not the term for it, but a term that doesn't have a solution that doesn't fit all the others. Okay, now, so that's why it's not only, see, this is a function of x, so this can't be 0 for any x that's in that interval of integration, for anyone. Okay, now if x is equal to x0, which is the place at which you're doing your initial condition, is any point in the interval, then a solution y of x of the initial value problem exists on the interval. So notice here, it's just that x0 has to be in the interval. All these have to be continuous functions of x, and the a sub n of x cannot be 0 for any value x in that interval. Okay. The other way of looking at that is, if it is, that defines your intervals. Okay. If your a sub 0 can't be a 0 here or here, then you have to be somewhere out there, in between here or somewhere there. It defines your intervals. Okay. Another way of looking at that. All right. So here's example 1. Unique solution of an initial value problem. All right, here it is. 3y triple prime plus 5y double prime minus y prime plus 7y equals 0. Okay? Now, we know that y at 1 is 0, y prime at 1 is 0, and y double prime is 0. Are those enough initial conditions? Yes, your maximum derivative is the third derivative, and you have 3 initial conditions, starting with y, ending at y double prime, not y triple prime. Now, guess what? Okay, we can look at this and say, hey, we know one solution. Y is equal to 0. That would work everywhere. Y is 0 here. The first derivative is 0. The second derivative is 0. The y is 0. First derivative is 0. Second derivative is 0. The third derivative is 0. Everything's a 0 here. So there's a y is equal to 0 is a solution. But because this third order differential equation is linear, there's no cross terms here, no powers other than 1, okay? All the conditions are met. This is a linear. The coefficients are functions of x alone. This 0 is a function of x alone, not a function of anything, but okay. So all the conditions, let's scroll down too far, all the conditions here are met. Okay? Your A's are all continuous. 0 is continuous everywhere. G is, yeah, that 0 is continuous everywhere. On any interval I, from negative infinity to positive infinity, the constant function 0 is continuous everywhere. Now, a sub n of x is not 0, of course. A sub n is the constant 3. These a's are not 0, but they are continuous. Okay, I'm sorry, I probably said that wrong. The a's are continuous. That's a constant 3, a constant 5, a constant -1, a constant 7. The g is the constant 0, is what I was meaning to say. But your solution is that. But because it's a third order linear differential equations with 3 conditions that are met here, everything here, if x equals x0 is any point on the interval from -infinity to positive infinity, that's going to be fine. And your x sub 0 is, of course, 1. And 1 is on from minus infinity to positive infinity. So that's fulfilled. Everything's fulfilled. Well, guess what? Since this is a solution, an obvious solution, and all the conditions are met, that means it's the only solution on any interval containing x equal 1. Wherever you go there, it would be. Okay. Took way too long to do something that simple. Let's look at example 2 now. All right. Now it says you should verify that this one, y is equal to 3e to the 2x plus e to the minus 2x minus 3x, is a solution for this initial value problem. Y double prime plus minus 4y equal 12x, when y of 0 is 4 and y prime of 0 is 1. Okay, they said verify it. Let's go verify it. Okay, unless you think that's too trivial to verify. What you think? Okay, now I'm going to try to move this taskbar out of the way as much as possible. So then I will try to move the whiteboard as much as possible to get maximum viewing pleasure. Okay, looks like, whoa, yeah, I guess I did it adequately. Okay, let me get my Wacom board down here and my stylus. Okay, now, oh, here comes Corbin. Okay, all right, Corbin's here. All right, I hope you're in by now, Corbin, but we're on in chapter 4, higher order differential equations, 4.1, preliminary theory, linear equations, and example 2, we're just starting. Now, here's what they've told us so far. Okay, example 2, they give us a solution. Y is equal to, and try that second part of an equal sign sometimes just doesn't show up. Okay, is equal to 3e to the 2x plus e to the minus 2x minus 3x. They say verify that that is indeed a solution to this differential equation. Let's see if I can get it in here. Y double prime minus 4y is equal to 12x. Okay, I know it's been a long time, but do you remember how to verify a differential equation? Maybe I should put a comma here. Oh, I forgot this. With these initial conditions, I put the comma, I remembered I had more commas to come. Y of 0 is equal to 4, and y prime of 0 is equal to, now neither one of my equal signs are working, 1. Okay, so there's our differential equation, and there's what they say is the solution. They say verify it. Now, this sort of irritates me. Why don't they go and tell you how they got this, and then you can go back and do the other things? But no, they string it out. They do things in reverse order first and then come back and do it. So let's do it. So what's the first thing we've got to do? Take a derivative. Y prime would be what? 6 e to the 2x. You take the derivative of e to the 2x, it's e to the 2x, chain rule, times 2. You had a coefficient of 3, 2 times 3 is 6. Got it, everybody? Okay. Take the derivative of this one, you're going to get a minus 2 times e to the minus 2x. Right? Okay. Derivative of the last term, minus 3. Perfect. Okay. But we also need a second derivative because that's what we got here. We didn't have a first derivative, but you can't get the second until you take the first. So that was not totally wasted, but we're not ever going to use it again. I don't think. Yeah, we will. We will. Sorry. Y double prime would then be what? You tell me. 12 e to the 2x. Right? Perfect. Okay. And that would be it. Exactly, because the derivative of the constant is 0. So let's do with what you just gave me. Okay. The y double prime is 12 e to the 2x plus 4 e to the minus 2x okay, minus 4 times your y. Now can I go on and do it? The minus 4 here is going to multiply by every term here. I can't get my pen to stay in place. Okay, there it is. Every term there. So I'm going to multiply them as we go. So minus 4 times 3 would be minus 12 e to the 2x. And then this minus 4 times e to the minus 2x would be a minus 4 e to the minus 2x. Okay, and this minus 4 times a minus 3 is going to be plus 12 x, right? Now, that's supposed to equal 12x from up here, right? We did the y double prime, we had minus 4 times y prime, and then we set that equal to 12x. And sure enough, it doesn't take much to show this and this add to 0, this and that add to 0, 12x equal 12x. But we're still not through. Your initial conditions must be reached. So let's go over here and plug in 0 for x, and you get y is equal to 3, e to the 0 is 1, plus 1, because e to the 0 is 1, minus 3 times 0 is 0, and that sure enough is 4. First initial condition met in spades. Okay, let's do the second, and this is where we do need our y prime. It wasn't totally lost. Here's y prime here is equal to, plug a 0 in there, and you get 6 minus 2 minus 3. And that, of course, is 6 minus 5 is 1. Yes, the second condition is met as well. We have verified that is your solution. And because your coefficients here, 1, minus 4, and 12x, if I can get it to move, there it is, 12x are all continuous functions on any interval whatsoever, from negative infinity to positive infinity, and that 0 your x sub 0 is on that interval from minus infinity to infinity. This is a unique solution. You don't have to look any further. You don't have to see if there's any other extraneous or other kinds of solutions that may work. This works, okay? And that's the only one that does. So now for that to be true, it must be a higher order linear differential equation with initial conditions, with the appropriate initial conditions. Okay. I think we've done everything example 2 wanted us to do. Let's see if there's anything else that example 2 wanted. So let me come down here and do a new share back to our book. It's over here. Okay, here we go. All right, so we did verify it. Okay, now that solution is linear. The coefficients as well as g of x are continuous. They're either constant or a polynomial, monomial in fact. Continuous everywhere. The leading coefficient is not 0, it's a 1, and it contains any interval containing 0, positive to negative infinity. Yep, done. We conclude that then is your unique solution. There are no others. Look no further. All right. Now, the requirements of that theorem, the a sub I, all your a sub I x's, all your coefficient functions be continuous, and that first one, not 0, for every x in the interval. They're both important. Okay? Specifically, if that a sub n of x is equal to 0 for even just one little x in that interval, then the solution of the linear initial value problem may not be unique and may not even exist. So here's an example of that. For an example, we should verify, and that's what we'll do next, that this solution with an arbitrary value c here is a solution for this initial value problem. Now, it's rather bizarre they would have a c here, because usually you look for a unique solution. Okay, this makes it a non-unique solution because it says for any parameter c. So let's go and do this. So let's come down here and move our sharing back to the whiteboard. Okay, and of course Melissa's in the way again. So let me see if I can move us out of the way here. I think I'll move us a little further south out of the way just so I can see everything I might need here. Y'all can't see what I'm talking about, but I promise I'm talking about something. Okay, so what I needed to do was clear the drawings here. Okay, I really didn't need to move y'all to do it, but I just wanted to see that a little bit better. Okay, where were we? Yeah, here it is. Here is the proposed function. I started right on the screen, can't do that. Y, it's an ugly y, is equal to c x squared. Now this to me is sort of a backward way to show this. Plus x plus 3. We need to show that is a solution to this initial value problem. X squared y double prime minus 2x y prime plus 2y. Yuck. It'll go away in a minute. I'm left-handed. I write like this and my hand falls on a button and it makes it do weird things. Okay, plus 2y. The plus didn't show up there, did it? plus 2y. I forgot to turn on the light and it's just gotten cloudy and I can't read my book. Hold on just a moment and let me see if I can reach far enough without yanking. Yeah, okay. A little bit of explanation of why things were a little late getting started. I didn't have everything set up right. My last class yesterday was a physical science class. Started at 2:30 and we only went to 4:15 because I was going to give them 2 hours to work on the lab. It's supposed to be a 2-hour lab. So we did that, ended at 4:15, the class part, started the lab. And the lab was a fairly simple lab, so I wanted to give them all the time they needed, and they ultimately got everything done. Not everything, because they were going to have to do some stuff on their own. I wanted to make sure they all could find the websites they needed and do all the things they did. And I said, okay, I want to make sure you get everything you need done. Yeah, they got it. So I checked out. And one reason I was sort of happy to do that, I had a meeting that was supposed to have started at 4. Okay. Well, of course, I was still hadn't even started the lab at 4. So when I finally finished, and like I was explaining to Melissa, the Monday, Wednesday classes have been, or will be as of Monday, cheated out of 1.5 weeks of the short summer term that we have. So I wanted to get as much in as I could for that class. So we got I got them going on the lab, and then I went to the meeting. And that meeting went longer than it was supposed to go. And then as soon as that Zoom meeting was over with, I had another Zoom meeting that was supposed to have started at 5:30. And by this time it was like 5:45 or a little bit later than that. So I was trying to get in the second meeting and I couldn't get in. Whoever the host wasn't paying attention. And so I sat there for like 15 minutes trying to get into that meeting. Finally made some phone calls and stuff and was able to get in. And then that meeting ran till, I don't know, pretty late. And when I went to shut down from that last meeting, I noticed I had forgotten to turn off my recorder. Okay, so the recorder that I had used from my 2:30 class and the 4:15 lab, until that got over with, because I was in such a rush to get to the next meeting that had already started at 4, okay, and it was probably by this time at least close to 5. Rushed to get into that, I forgot to turn off my recorder. Okay, then I didn't even think about the recorder when I went to the second meeting. So the students in that class will get to hear all about Banner. No, all about our preparations of our Blackboard for virtual classes. They decided to make everybody do the same thing. Then they'll hear about the nominating committee from my church. Okay, that was the second meeting I was on. So before class today, I was trying to go through, and I was able to edit the thing in Screencast-O-Matic, but it had already gone to YouTube. So I was in YouTube trying to edit in YouTube. And everything it said to do, I did, and it kept being the same length. So that's why I was a little late getting everything set up for this class, because I was so frustrated with YouTube. It's just not clear. And I think that's why they say once it's out there, it's hard to get it out. I know there's ways you can cancel the whole thing. I couldn't figure out a way to do that. If any of you know how to do that, clue me in. But that's why I'm still getting things set up. Well, that's why we were late. You can what? Private? Is that what you said? Okay. Okay. That's what I was trying to do, but I didn't know. So Do you mind hanging on at the end of class, and I'll go there and you, okay, and you can show me how to do that. Remind me of that. Let me turn off my Screencast-O-Matic first, and then we'll do that. Okay, I appreciate that. Okay, so let's go to, all that came from realizing I hadn't turned on the light. That's why I was in such a rush, and the sun was brightly coming in the east window then, but it's not anymore. All right, where are we? Okay, here it is. So I've written down the differential equation. I hadn't put the equal 6. That's where I was getting hard to read. I realized the light wasn't on. Equals 6 with initial conditions, y of 0 is equal to 3 and y prime of 0 is equal to 1. Now, and it says on the interval from minus infinity to positive infinity. Okay. Now, on first glance, this may seem totally reasonable. Okay. Now, because your coefficient functions here, x squared is continuous everywhere from negative infinity to positive infinity. Minus 2x is continuous everywhere from negative infinity to positive infinity. The constant function 2 is continuous everywhere from negative infinity to positive infinity. And the constant number 6 is, that function is continuous everywhere from negative infinity to positive infinity. Okay, your initial conditions are at the same value. What's wrong with this picture? Right here. X squared can be 0, in fact is 0 at one point in this interval. Namely where? X squared is equal to 0 when x is equal to 0. So not only do we have a violation there, that's where we set our initial conditions at x equals 0. On a careful glance of this, I would almost say this has no solutions because nothing is correct here, you would think. But let's do. What they say to do is verify that this function here, the y function here, is a solution for this initial value problem, okay, with one exception. It says for any choice of the parameter c. I don't see how that's going to be true, but let's just see. So what we have to do, first thing, take a derivative. What's your y prime? Two cx, right? Plus 1. Okay. What's your y double prime? Okay, 2c. Okay. Now let's plug that in here, and you have x squared times 2c. So I'm going to put the 2c, I'm going to try to put the 2c out front. Okay. Minus 2x times y prime. Well, that would be minus 4c x squared, right? That's the first term. Minus 4c x squared minus 2x times 1. So that's minus 2x. Okay. And then we put plus 2 times what your y is. So that's plus 2c x squared plus 2x, okay, yeah, plus 2x. I should really be writing all the steps, but it's just so hard to write on this thing. Yuck, wait a minute. Plus 6, wait, the 2x didn't show up, plus 2x plus 6, and that is supposed to equal 6. Well, let's see. Here we've got 2cx squared. Whoa! I think I left off my minus, didn't I? Oh yeah, no, that's right. 2cx squared plus 2cx squared is 4cx squared minus 4cx squared. Those add to 0. 2x or minus 2x plus 2x add to 0. 6 equals 6. Yes, that's true. Now let's see if the initial conditions are met. Y at 0 would be, I think that's pretty obvious, y at 0 would be 3 times 0 squared is 0, or c times 0 squared is 0, plus 0 is 0, and that would be 3. Sure enough, that works. Let's do our y prime at 0, and that would be 2 times c times 0 would be 0, plus 1, that would be 1. That works. It looks like everything works like a charm. It does appear that for any arbitrary coefficient c, this will work. Okay? Any parameter c. Well, you would say, wait a minute, could that possibly be true? Okay? And okay. So we have verified that it seems like it works. Okay? Now let's go back to the text, which I'm trying to reach here. I have to hold my Wacom in place because I'm right on the edge of my computer here. Because if I go too far up on the keyboard, it keeps hitting keys and making noises. I don't like that. Okay. All right, here we go. Now, Melissa, you're in the way again. Why can you not stay out of the way? Okay. Let me see if I can find you here. There you are. You can't see this, but I can. Okay. There, Melissa. And Corbin, too. No. And I'm also. No. I don't know why. I won't let good well enough alone. Okay. It's out of my way so I can see everything now. Okay. And we still don't have anyone else trying to come in, do we? Nope. Okay. So where are we? We're right here. We have verified that this function seems to satisfy everything here on the entire interval from minus infinity to positive infinity for any choice of the parameter c. Hold on just a minute. Not only is it I needed light, I need the ceiling fan because it's getting stuffy in here with the door closed. And my wife insists I have the door closed. She's working here today. Okay. So we've done this. In other words, there's no unique solution for the problem. Well, you might say, are all our conditions met? No, they're not. That condition that this thing not be 0 for any... Oh, here comes Ricky. Good to see Ricky. Okay. All right, well, Ricky, are you here yet? Yeah, I see. Or you're still connecting to audio, so I'll wait just a moment and let you get connected. All right, Ricky is here now, I think. Okay, welcome back. How are things going?
I just got tested, so I'm waiting for the results.
Oh, okay, you're waiting for results. Okay, I thought you said, all right, well, good luck with that. Okay, are you feeling good? Good. Okay, well, that's good too. Okay, how's your dad doing? Okay, you don't need to answer if you don't want to. Okay, all right. Where we are, we're in Chapter 4, Higher Order Differential Equations, 4.1, Preliminary Theory, Linear Equations. And we've just been through, and by the way, it's, okay, so let me go up here. Let me use the right end of the pen. And we're talking about a theory that here it is. If you have a linear nth order differential equation, the a sub n's here are your coefficients for your nth derivative, the n minus first derivative, the n minus second derivative, the third derivative, second derivative, first derivative, and the constant, not constant, the y itself. And g of x over here on the right hand side, they're all continuous functions, okay, on some interval I. And this a sub n, the one that's the coefficient function for your nth derivative, that one can't be 0. And the reason it can't be 0 is that then you wouldn't have an nth order differential equation. You'd have an n minus first or something like that. And it has to not be 0 for every x that would make that 0 on that interval I. And then, of course, for your initial condition, the x equal x of 0 must be in that interval as well, okay? And if all those conditions are met, then the solution, y of x, of that initial value problem exists. You guarantee you're going to have a solution. And not only that, it will be a unique solution. And we just verified that with example 1. And now we're coming down to do example 2. If I can get my pen to come over. Here we go. Whoops, went too far. See, what I did was accidentally touch the screen. There we go. Here's example 2. Am I on the right? Yeah. No, we've already done example 2. Sorry. We were doing this thing that followed example 2. All right. We've just shown that this is a solution. Now that has an arbitrary parameter in it, which we weren't supposed to have. It's supposed to be, if you have a second order differential equation, second order differential equation, linear, or not linear, coefficients only of x, with a second order linear differential equation, okay, with all the coefficients being continuous and everywhere. This should be a unique solution, and yet we have any choice of parameter. Now, why is that the case? And we just verified all this, okay? There is no unique solution, and we look at this and say, well, wait, all your conditions are satisfied except the most obvious difficulty is that your a sub 2 here is not non-zero for every value of x, from negative infinity to infinity. Okay? Specifically, it's not at 0. I mean, that's equal to 0 there. So therefore, this condition was not met, that the a sub n could not be 0, any value there. Now, if you had said from any value from, not counting zeros, any positive value, that would work. Any negative value, that would work. You just cannot include 0. But of course, your initial condition was at 0, so that's a double whammy there, okay? The initial conditions were imposed at x equals 0. No wonder we came up with a non-unique solution. All right. Now, something we mentioned before, we're going to mention again here, and this is boundary value problems. So the point of that whole discussion is you got to make sure every condition of that theorem was reached, including that leading coefficient cannot be 0, okay, for any value x in the interval. So now let's deal with the boundary value problem. Another type of problem consists of solving linear differential equations of order 2 or greater, in other words, a higher order linear differential equation, in which the dependent variable y or its derivatives are specified at different points, not the same point. Initial condition, they all have to be at that same x0. And here would be an example. A sub 2 of x times the second derivative. Why is this so jumpy? Second derivative of y with respect to x plus a sub 1 of x dy dx plus a sub 0 of x y is equal to g of x. Now, again, as long as a sub 2 of x is a continuous function everywhere on the interval, a sub 1 of x a continuous function everywhere on the interval, a sub 0 of x a continuous function everywhere on the interval, and g of x a continuous function everywhere on the interval. Okay? But here's the problem. Okay? Your one condition is y of a is equal to y1, not y0, but y at b is y1. Okay? That's a boundary value problem because you're not taking those functions at the same values. Okay? That's a boundary value problem. And the prescribed values are called the boundary conditions, just like we called them the initial conditions before. A solution of this kind of a problem is a function satisfying the differential equations on some interval I containing a and b. These are the two x values, okay, whose graph passes through those 2 points, ay0 and by1, okay. And you see, I don't think this is a particularly great graph. Well, yeah, it is. Okay, this shows a bunch of solution curves, okay, that may satisfy the initial condition. I mean, not the initial condition, the differential equation here. But to meet these boundary conditions, here's one that x equal a is y0. Here's another that x equal b is y1. See, those are completely different functions. So you do not have a unique solution. There's one, there's another. And if you happen to have some other one that also fit that differential equation, and maybe it did, you might have, I want to say an infinite number, but you can have more than one. And if you have more than one, not a unique solution. Now, for a second order differential equation, you can have other pairs of boundary conditions. Notice this one was y at a is y0. You could have also had y prime at b is y1, and that's the one they give here. Or you could have had y prime at a is equal to y0 and y of b is equal to y1. That's the one they give here. Or you could have y prime of a is y0 and y prime of b is y1, and that's the one they give here. Okay? Now, they don't always have to be the same values. They're just giving different illustrations. Okay? But you would have 2 points, and either the function value or its derivative would be defined at those 2 points. But obviously you can have multiple solutions then. These 3 pairs of conditions are just special cases of this general boundary condition. Okay, now this is a bit bizarre, but it's true. Alpha 1 times y of a plus beta 1 times y prime of a is some gamma 1. Wow. Alpha 2 of yb plus beta 2 of y prime of b is some constant gamma 2. Okay? Now they throw these out, they introduce them to you. I don't think we'll ever see them again. But they're just telling you these are boundary value problems. They do not have unique solutions. Okay? This next example shows that even when the conditions of theorem 4.1.1 are fulfilled, a boundary value problem may have several solutions, okay, as shown here in this figure here. This shows two, but it can have several solutions of the same boundary values, okay? Or it could be a unique solution, and that's fine too. Or it may have no solution at all. Everything else seems to be fine, but it may have no solution at all. So let's move on down, come on down to here, and let's do example 3. Okay. Now, I don't know if you remember, I sure don't, example 9 in section 1.1. We saw a 2-parameter family of solutions. Yeah, I remember this. Excuse me. X double prime. Now here the independent variable is t, not x, so don't get confused there. X double prime plus 16x equals 0. That has this as a solution. Okay. X is equal to C1 cosine 4x plus C2 sine 4x. Okay. If you want to go back and check that, you can see it's a second order differential equation right here, 2 parameters, so it's a 2-parameter family. Notice there's no initial conditions given here yet. We're going to get to there in a minute. So suppose we now wish to determine the solution of the equation that further satisfies the boundary condition. X of 0 is 0 and x that pi halves is 0. Okay, so let's see what we can figure from there. Observe that the first condition, when you plug that in, and I think we'll go back to our whiteboard. Okay, and let's see if I can clear this. Now I want to get us out of the way again, so let me move us back over here as much as possible. Okay, and we haven't added, no one else is waiting, are they? Come on, where are you, Pen? There you are. Nope, just the 3 of you. That's good. Glad y'all are here. Okay. Okay. So let me write down what we have. Oops. I always want to go to the screen because that's how I'm used to writing, but not now. X is equal to C1 cosine 4t. Oh wait, I should have written the other first. All right. Cosine 4t plus C2 sine 4t okay, that is your solution. I've got them backwards from what they do in the book, of this differential equation. X double prime plus 16x is equal to 0. Now, they didn't say verify it, but it's really not that bad to do. Okay? If you think, what's the first derivative of this? That would be a minus 4 C1 sine 4t plus 4 C2 cosine 4t. Second derivative would be another 4 times that, so that would be a minus 16 C1 cosine 4t. The next one would then be a minus 16 C2 sine 4t, and then when you do that double prime, which has 16s and minuses, plus 16 times this, yeah, you have exactly 0. Okay, so that does seem to be a solution. Now, here are the boundary conditions they give. Okay, I started to write it in the wrong place. X of 0 is equal to 0 and x of pi halves is equal to 0. All right. Now, let's go back to our solution here. Somewhere here. There it is. Okay. And plug in x of 0. And we know that the value x should be 0. So is 0 equal to, and when x is equal to 0, cosine of 0 is 1. So that would be C1 plus, but sine of 0 is 0. So here we have our C1 being 0. Okay, fine. Let's do the second boundary condition, x of pi halves. And we know it's supposed to be 0. And that would equal, we already know C1 is 0, so we won't even write that down. C2 now, when x is pi halves, t is pi halves, multiply pi halves times 4, and you get 2 pi, right? And sine of 2 pi is also 0. So the C2 disappeared. No, I said that wrong. Yeah, well, you don't get the C2, the whole term disappears. So guess what? You don't have so C2, it remains your arbitrary coefficient. This just gave you 0 equals 0, so your solution is x is equal to, this would be not C2, this would be a 0 here, because C1 was 0, and this would be 0, so 0 equals 0. That tells you nothing, so you're left with x equal C2 sine 4t. That's it. There is no unique solution. It's an arbitrary solution for any value of C2. Okay. Now, let's just change our boundary conditions. Same equation, changing the boundary conditions to be, now I'm going to try something here and you may or may not like it. Let's see. I think it's under format. If I could get the pen to show up. There it is. Okay. Now, can you pick a color other than black and white? Red? Okay, let's go with red. This next condition is going to be x of 0 is equal to 0. That's the same. But this time we're going to say x of pi eighths is equal to 0. Okay. Now, your first condition there is going to give you the same C1 equals 0. The second condition gives you this. X equal C1 you've already determined to be 0 plus C2 times, now when you plug a pi eighths in for t, 4 times pi eighths is pi halves, and sine of pi halves is 1. So you get the x 0, I put the x down, 0, that's the x value there at pi 8 was 0. So this gives you that C2 is also 0. Well, guess what? C1 was 0, that still holds, okay, in the red as well. And C2 is equal to 0, you have no solutions, okay? X equals 0 is your only solution, okay? And that's pretty obvious that x equals 0, x prime is 0, x double prime is 0, so your trivial solution is a solution, and it's the only solution, okay? So that gives you a unique solution. So I said it wrong. It is a unique solution, okay? Now, C, we're going to change, keep the differential equation the same. Okay, we need to go to a different color here. And you pick another color other than white, red, or black. Blue, you want Carolina blue or dark blue? A little louder? Carolina blue. Oh, well, it didn't like Carolina blue. It must be for NC State. Okay. Or Duke. Okay. Yeah, Duke is the dark blue. Okay, never mind. All right, let's come down here and have your new initial conditions. Guess what? The x of 0 is still 0. There's your first condition. That's going to produce a C1 equals 0. So that's going to work wherever my pen is here for here as well. Okay, but then the second condition here is x at pi halves is equal to 1. Now that's a boundary value, perfectly fine boundary value. Okay, now let's see what happens now. We already know that your plugging at x equals 0 is going to produce C1 equals 0. Okay, the second one is that x is going to be 1 when you plug pi halves in for t. You already know the C1 is 0, so plug a pi halves in here. 4 times pi halves is 2 pi, just like before. And sine of 2 pi is equal to 0. So here you get 1 equals 0. And when is that ever true? Never. Ever. Okay? And yet that's what your boundary value told you it needed to be. Well, it's not going to work. This one has no solutions. You will not find a solution that fits this differential equation in this form, which that's what your analysis will tell you, with that boundary condition. Not ever going to happen. So with some boundary conditions, you can have an infinite number of solutions. With some boundary conditions, you can have absolutely one and only one solution. And with the other sets of boundary conditions, you may have absolutely no solution to work. And that's what we've just shown. Now we're moving, so let's move back to the book. Any questions on that before we leave it? Okay, trying to get this to now. May wind up with people in the way again, but let me see if I can come down here and scroll down. We've just finished all that. Whoops! I should have known. Okay, what I'm going to do is try to scroll this down a little bit here. Okay. Okay. Now, here we're going to talk about a term that we've used before, but we're not going to use it in the same way anymore. Okay, I'm I'm going to need to move people to the top. Okay. Y'all can't see that, but it was in the way. Let's see, we've been going at it for about an hour, close to an hour and a half now, because I was in such a rush this morning trying to get YouTube to do what I wanted it to. I didn't take enough time. I need to do a quick bladder break. Do y'all object? Break as well. I wore these for my 2 classes, long classes, and 2 meetings yesterday. My ears got very tired of having these on. And I can tell they're still not too happy with it today. Okay. So now we're using, can y'all hear me again? Because I'm sounding a little echoey to me. Okay, good. All right. Okay. Now we're going to use a similar term from what we've used before, but for a totally different meaning. Homogeneous equations. Here is what we mean by that in nth order differential equations. Anytime you have the a sub n with the nth derivative of y with respect to x plus a sub n of x, n minus 1 of x, some other function of x, times the n minus first derivative of y with respect to x, and count on down till you get a sub 3 of x times y triple prime of x plus a squared, a sub 2 of x times the second derivative of y with respect to x plus a sub 1 of x times the derivative of y with respect to x plus a 0 of x times y. But when that g of x over here is a 0, you now call that a homogeneous nth order linear differential equation. Has nothing to do with the degrees of your x's and your coefficients. That's, well, actually the x's and y's, okay? When we're talking about homogeneous coefficients, that meant that your total degree of your x's and your y's, or whatever your variables were the same for every term. That's not the case here. So, because guess what? Your y's can only be of one term, of one power. So we're not even talking anything about that. Has nothing to do with the a sub x's. All it has to do with is that 0 at the end. That makes it an nth order, linear nth order differential equation, homogeneous. That 0 at the end. Now, whereas in general, everything else can look exactly the same, but if you had anything over here, g of x, that g of x could be a constant, as long as it's not 0, 7, 3 halves, 1, -1, whatever, pi fourths, you know, whatever that, if that's a constant, that's not homogeneous, that's non-homogeneous. If it's any other function of x, e to the x, sine x, anything with an x in it, that's not homogeneous. If it's a 0 and a 0 only, is it a homogeneous differential equation. Okay. The word homogeneous in this context does not refer to the coefficients that are homogeneous functions, that as in section 2.5. So that's what I kept trying to say. Okay. Now, we will see that when we're trying to solve an equation like 7 here, that does have a g of x at the end, we first go back and replace the g of x with a 0 and solve the what they call the associated homogeneous equation that looks just like this one, except instead of a whatever function you have here that was not 0, replace it with 0. Okay, so that's why we're doing this, because to get to the general case, which is this case here, we have to do that one first, the homogeneous, the associated homogeneous equation. Now this works for linear higher order differential equations. So to avoid needless repetition throughout the remainder of the text, we shall, as a matter of course, make the following important assumptions when stating the definitions and theorems. Number 1, the coefficients a sub I of x are all, and g of x also, are always continuous, just like we had before, and the a sub n of x is not 0 for any x in the interval of your definition of that differential equation. Okay, now here's another thing they're going to introduce here. Okay, so they just tell you what homogeneous and non-homogeneous are. We're going to leave it for now. Come back, we're going to be dealing with those associated homogeneous equations. Now they're getting sort of to a slightly different topic, and this is on differential operators. Now, as if we didn't have enough ways to express a derivative, we have the Leibniz notation, d by d. We have the prime notation, up to a certain place, and then you put numbers in parentheses. Yeah, let's have another way to express a differential operator, okay? In calculus, differentiation is often denoted by the capital D, okay? And I don't know if you remember back when you did partial fractions, a technique for solving, for integrating rational expressions. It was called partial fractions. And if you did, I know if you had some authors, if they were choosing the arbitrary coefficients, they would choose A, B. A lot of times that's the only ones they need. But if they needed a third one, they do C. If they needed a fourth one, they jump to E. And the reason is, now some books may not do that, but some did, and the reason is they avoid that differential operator, even though you weren't talking about differential operators. So here's what that D stands for. It just stands for d by dx, or d by dt, or d by d, whatever your independent variable is. That's what the D stands for. And then whatever you're operating, the function you're operating on, that goes to the right of it. So dy, capital dy, mean dy dx, okay? Or dy dt, or whatever your independent variable is. So that symbol D is called the differential operator because it transforms a differentiable function into another function. Now wait, what do you mean by that? Okay, here's what they mean by that. So d of 4 of x is, d of cosine 4 of x is take the derivative of cosine 4x, and that gives you minus 4 times the sine of 4x. That was in a previous problem. D of 5x just means take a derivative of it, and that would be 15x squared minus 12x. Exactly. That's all it means. It's just another way to write it, so you don't have to do your d by d's. Okay? The higher order derivatives can be expressed in terms of that d operator also, because this was d2y dx squared actually means d by dx of y. So here you have two d by dx's of y, d of y, and that's t squared of y, or that's how they write it. That doesn't mean squared, it means operated twice. So in general, dn dy over dx to the nth is d to the n y, where y represents a sufficiently differentiable function. It has to be a function that you can differentiate at least n times. Okay? And what that gives you, especially with linear differential equations, the polynomial expressions involving that d that you get out of that, like this one up here was, well, okay, they don't have any like it. D plus 3, that would be, if you did d plus 3 of y, that would be dy dx plus 3y, okay? This would be y double prime of x plus 3y prime minus 4y, okay? You just put your y's in that term. But notice what you get here, which you have linear expressions like that, okay? Even when you have x's in them, then the 5x cubed, that would be your a sub n, a sub 3 here, okay, times d3 minus 6x squared d2 plus 4x plus 9. Those are all differential operators. So in general, we define the nth order differential operator on a polynomial operator or a polynomial operator to be, and here they introduce another letter. Now don't let the letters get you down. Frankly, I think they're confusing, but when you're actually doing the stuff, you don't really even think about them, but you could use them. Now that linear operator means that your a sub n of x, that would be just like your 5x cubed here, okay, times d to the nth, where n is your maximum derivative you're taking in this problem, plus, and there's your coefficient function d n minus 1 plus blah 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 all the way down to a sub 1 d plus a sub 0 x. Now that whole operator operates on a y, okay, because your y goes in here and here and here and there, okay. Now notice they call it a linear operator. It's linear in the d's, because you don't ever have, remember that the n's here don't stand for powers, they stand for the number of derivative, the nth derivative, n minus first derivative, and so on. They're not standing for powers, so there aren't any d sub n's multiplied by d sub n minus 7, you know, or d2 times a y, you know, a dy, a d, you know, a first derivative. Okay, you don't have any of those, so these are linear. That's why they call it linear operator in D. Not necessarily in X, they could be anything. These are not linear in X up here. These are linear in D down here. As a consequence, the two basic groups of differentiation, the two basic properties of differentiation, the derivative of a constant times a function is the constant times the derivative of a function, and the derivative of the sum or difference of two functions is the sum or the difference of the derivatives of those two functions. The differential operator L possesses the linearity property, and that's why they call it a linear operator. Okay, that is, L operating on a linear combination of two differentiable functions is the same as the linear combination of L operating on the individual functions. Blah, 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 blah. Okay, so let's scroll on down, and this is the summary of what they were just saying. Okay, so if you have L operating on a constant times a function plus beta, another constant beta times a different function, as long as all these functions are differentiable, L is your differentiable operator, the linear combination of those differential operators, then this would be, you can pull the alpha on the outside of the L and just have L operating on F plus beta times L operating on G. Remember, the L operators are your linear combination of your differential operators. These alphas and betas are constant, and because of this 9, we say that nth order differential operator L is a linear operator. Basically, these two features here guaranteed this. This summarizes them put together. All right. Again, a lot of blah, blah, blah that we basically seldom use. I mean, we will come back and use it a little bit, but most of the time it just becomes pretty intuitively obvious. Oops! Intuitively obvious, that's what we're meaning. Okay. This is driving me nuts here. Where did it go to now? Okay. I'm not sure where we are. Let me keep going up a little bit. Wait, I have a split screen now. How did I do that? Does anyone know how to undo that? They might be good for some purposes, but not for what I want them now. Are any of you familiar with how to undo a split screen here? I don't know how I got it to happen. I didn't want it to happen. That didn't do it. Say again, wait just a second. Let me get my, okay. I can't hear you. Escape? Okay, let me, I need to get back to where I was. I think that's where I was. Well, no, I've lost my, are you just seeing a black screen or something like that? You do. Okay, I can't find my book again. It's, I don't know what they did with my book. I thought it was this screen here, but nothing's showing up. Let me hit escape on my keyboard and see what happens. Okay, now let me resume share and see if that does it. Okay. All right. I think I'm going to have to go back and get my book again. For some reason, it lost the book. So let me come down here and go back and get my book to come back up again. Okay, now I'm back to a split screen. And you say hit escape now on my keyboard. Okay, nothing happens. Can you still see the split screen? Maybe it's because I'm not. Oh, really? See? Okay. Okay. Now if I hit escape, it should leave it. Nothing happens when I hit escape. Okay. That's a good try. Yeah. Well, I can get the arrow and bring it all the way to the bottom. Would that do it? Okay. That sort of dismisses the bottom one. I was going to try that earlier, but I thought I would try to escape first. I don't know if I did it or not, but it worked. Okay, now I've got to find out where we were again. This is what happened. Yeah, I'm getting close to where we were. Nope, I'm not. Yuck. Okay, here we are. I think this is where we were before. Okay, now I need to get out of this. There. Good. I don't know what those things mean, but I don't want to be there. Okay, now what I was trying to do before was get us down here, and my pen went its own direction. Okay, we finished with linear operators, which we basically was a lot of blah, blah, blah that was, we will sometime use them. Now, differential equations. That's what the whole course is about. Any linear differential equation can be expressed in terms of the denotation. Sure. For example, here's one that, no, it's not one we had before, but it is one. Y double prime plus y 5y prime plus 6y equal 5x minus 3. Okay? Well, that means a D2, that means a D1, that means a 5D1, and that means a 6. So we can write it as D2y plus 5dy plus 6y is equal to 5x minus 3. See, it doesn't change anything over here. Or factor out the y, you might think of it, and now your differential operator is d2 plus 5d plus 6y is equal to 5x minus 3. Okay? Now, I don't want to go up and find 8. That was something we were doing not too long ago. that's up at the very top of this page, not at the very top, but near the top. That's that linear operator when they defined L. Okay, that's all it was. It says using 8, which that defined that L for us. Okay, we can write that linear nth order differential equation. And now the 6 was the one that had equal 0, and the 7 was the one that had equal g. So this has really nothing too much to do with this one, though we will use it again. This is your homogeneous form. This is your non-homogeneous form. It's just saying you can write that the left-hand side of your general linear differential equation as an L of y, always. Now, again, blah, blah, blah. Now, totally new concept here, so I think I'll get those L's off the screen. I thought I was doing that before, but I didn't go far enough. This is the next concept. Yuck, here it did it again. Okay. Tell you what, this is the time I'm going to come back and use my finger, because this Wacom is just a little too sensitive, or not sensitive enough at other times. Okay, so I'm going to use them. Okay, here is an important one you do need to keep up with: the superposition principle. Okay, now we go to 10:45, so we have a little under a half hour to go. Let's see what we can get done. In the next theorem, we see that the sum, or think superposition, of two or more solutions of a homogeneous linear differential equation is also a solution. So basically what we're saying, if you have a solution, you know it's a solution. Not saying a unique solution, just a solution for the differential equation. And this is a homogeneous linear differential equation. Then you find another solution that works, then the sum of those is also a solution. And that theorem is called, that principle is the superposition principle for homogeneous equations. So let's let y1, y2, y3, all the way up to yk be solutions of a homogeneous nth order differential equation that's homogeneous. That's the 6 here. That's why they say homogeneous there. On some interval I, then the linear combination of those, y is equal to c1 times y1 plus some c2 times y2 plus some c3 times y3, all the way up to c sub k times y sub k, where ci's are i's going from 1 to k, arbitrary constants, can be anything. That's also a solution. If those y's were a solution, then any linear combination of them will also be a solution. Okay? Now, they do a proof here using the L, and I'll let you read through the proof. We just don't have a lot of time to be doing the proof. And let me see if I can scroll down here without making a mess here again. Trying to be very gentle with that. Okay, here's a corollary to that theorem. Yuck! Why did it do that? Forget this Wacom. Okay. Well, I can't get it to move now. Why won't it move? Well, okay, I see. I'm pushing the wrong button. Okay, I'm using the right key rather than the left key. Okay, here's the corollary. We may not ever get there. Okay. To that theorem. Now, a constant multiple, okay, y is equal to c1, y1 of x, is a solution of a solution y1 of a homogeneous linear differential equation is also a solution. So you don't have to do them all, just one. If you know y1 is a solution, then any arbitrary constant times that y1 will also be a solution. Okay? Here's a second corollary. A homogeneous linear differential equation always possesses the trivial solution y is equal to 0. Now if you think about that, yeah, of course that's true, because all your coefficients there are x's, but if your y is equal to 0, the y prime is equal to 0, and y double prime is equal, all your y primes are equal to 0 if it's a homogeneous linear differential equation. Sure, that's going to equal 0, no matter what your c's are or anything else. Okay, so this is not true for a non-homogeneous, definitely not, but for a homogeneous it is. So here's example 4. I think I'll scroll on down and let's see if I can do it better this time. So far I've been very poor at this. Okay, I feel good about myself. Here's example 4. The functions y1 is equal to x squared and y2 equal x squared log x, they say are both solutions of a homogeneous linear equation x cubed y triple prime minus 2x y prime plus 4y equals 0, homogeneous there, linear, okay, on the interval 0 to infinity. Notice the 0 has a parenthesis in front of it, meaning we cannot allow 0 to be a solution. Doesn't that seem pretty obvious that if this is a solution, you can't take the log of 0? So obviously 0 has to be excluded, nor can you take the log of a negative number. So all the negative numbers have to be excluded. So therefore we're only dealing with positive x's. Okay, slightly positive, yes, but all positive. No zeros, no negatives. Okay, now if those are both solutions, they didn't tell us to verify. Did y'all want to verify that? If you do, we can go to the whiteboard and do it. Let me know. Yay or nay? Say again? Okay, all right. They're pretty easy to do because when you take especially that first one, the triple derivative of that would be 0, and anyway, well, we'll just go from there. Okay, now by the superposition principle they just told us, if both of these are solutions, and we're taking their word for it, they are, okay, then any linear combination of them is also a solution. Now, I'm trying to think what we're supposed to do with that. I guess that was it. There's nothing to work out. They just said if these are solutions, that's also a solution. Psst, done. That wasn't much of an example, I guess, but maybe that suffices. Okay, so let's move on to the next little vignette here. Okay, now here's a function, y is equal to e to the 7x, and they tell you it's a solution for y double prime minus 9y prime plus 14y equals 0. Now, they don't say verify it, but they do say because that differential equation is linear, yeah, y double prime minus 9y prime, the 1 is a linear, well, it doesn't matter, it's linear, okay, and it's homogeneous, okay. The constant multiple c times e to the 7x is also a solution, okay. Yeah, that was your corollary. For various values of c, we see that y could be 9e to the 7th x, 0, negative square root of 5 times e to the 7x. They're all solutions for the equation. That's basically that corollary. For any c you multiply by a constant c, then those are also solutions. Now, jump another rabbit here, okay? Even though we've mentioned the term before, and we'll mention it over and over again. Okay, I'm sorry. If I press too hard on this, it starts making noises. Okay. Now a whole new, oh, there it did it. The last strike does it. I'm not going to mess with that again. I'm going to come up here. I will mess with it again because I'm stubborn, but okay. Linear dependence and independence. Okay, we got about 15 minutes left. Okay. The next two concepts are basic to the study of linear differential equations. Linear dependence and linear independence. So, what you have, a set of functions, f1 of x, f2 of x, f3 of x, f4 of x, all the way up to x sub n of x. Okay, they're all functions. If that set of function is said to be linearly dependent on some interval I, if there exist some constants, c1, c2, c3, c4, all the way up to c sub n, one for each one of those functions, not all being 0, okay? Some of them could be zeros, but not all of them zeros, such that if we combine c1, multiply it by f1, plus c2 times f2, plus c3 times f3, plus c4 times f4, plus c sub n, all the way up to c sub n times f sub n of x. If you can find a set of c's that are not all 0, that you can make that true, then bingo. Oops, you can't say that in Alabama. Then not true, that would be true for every x in the interval. Then the set of functions is not linearly dependent. Because what that's saying is you can come up with a linear combination of those functions to be 0. Okay? And if that's the case, they're not dependent anymore. Because they're dependent functions. What you could do was pull one of those functions out. Okay? One of these functions out, subtract it, put it on the other side, and then you would see this function here is a linear combination of all the others. So therefore it would be linear dependent. Now of course if all those c's were zeros, then they're linearly independent, because if you can't come up with a combination of c's, not all 0, then there's no way you can combine those together to get 0 unless all the c's were 0. So if a set of functions is not linearly dependent, it's called linearly independent. Okay. Seems like a very circular argument, doesn't it? Well, here's some other words that probably also sound circular. In other words, a set of functions is linearly independent on the interval I if the only constants for which you can make that combination, c1 f1 plus c2 f2, so it's 3 f3, all the way up to cn fn. The only way you can get those n functions to add to be 0 is if every one of those c's is equal to 0, then that set of functions is linearly independent. Now it's easy, they say, I always am suspect when the book says, it's easy to see, okay, it's easy to understand these definitions. Okay, let me not go quite so far. Come on, where are you? There you are. All right. It's easy to understand these definitions. What did it just do? All I did was set down my Wacom and it jumped. So evidently some other key makes it move too, and I just don't know which key it is. Okay. It's easy to understand these definitions for a set consisting of two functions, f1 and f2. Okay? If the set of functions is linearly dependent on the interval, then there do exist constants c1 and c2, both not zero, so that for every x on the interval, c1 times f1 plus c2 times f2 is equal to 0. Dependent if both of those c's are not 0. Therefore, we assume that c1 is not equal to 0. It follows that f1, if you know that that c1 right here is not 0. Okay? Now, why do I have a hand there rather than a pointer? I don't know. Not used to that. Okay, that c1 is not 0. Okay? Then what we can do is solve for f1 by subtracting c2 f2 from both sides and then dividing by c1. That's legal because c1 is not 0. Well, now you can see that f1 would be some multiple of f2. In other words, minus c2 times c divided by c1 times f2. That is, if a set of two functions f is linearly dependent, then one function is simply a constant multiple of the other. That's if you only have two functions. That's going to be the case. So if you had one line here, a constant multiple of that would either be here or down here or somewhere else, but identically the same line, just, I'm sorry, I'm sorting it wrong, a multiple of the other one. Okay? That's what that means. If they're independent, if they're dependent. Okay. Conversely, if f of 1 of x is equal to c2 f2 of x for some constant c2, then minus 1 f1 plus c2 f2 equals 0 for every x in the interval. So therefore, if one is a constant multiple of the other, then they're going to be dependent. Okay. They're going round and round with this. Hence, a set of functions is linearly independent because at least one of the constants, namely c1, is not 0. If we conclude that a set of two functions, f1 and f2, are linearly independent when neither function is a constant multiple of the other on the interval. Now again, we're only dealing with 2's. For example, f1 is equal to sine 2x and f2 is sine x cosine x. They're dependent on each other. Okay? And why is that? Because if you remember from your trig identities, sine of 2x is exactly 2 sine x cosine x. So there you found a multiple of one that was equal to the other. On the other hand, if f of x is equal to x, that's this function here, this function here, and again, I don't know how I got a hand here rather than a pointer, but anyway, if that function f1 of x is just the function x, but f2 is the absolute value of x, which is this function here, they are not linear multiples of each other. They're not. There's no way you can get one from the other on that interval. Now, if you restricted your interval to 0 to positive infinity in both cases, yes, they're exactly the same function, okay? But not if you include all real numbers, okay? They are linearly independent on the whole number line, negative infinity to positive infinity. It follows from the preceding discussion that the quotient f2 divided by f1 is not a constant on which the on an interval in which the set is linearly independent. That little fact will be useful in the next section, if we ever get there, it feels like. So let's scroll down. I think this time I'm not even going to mess with the thing, and let's just go on down to example 5. so much. 7 minutes. Okay, let's see if we have time to do this. Here's a set of functions. f1 of x is cosine squared x. f2 of x is sine squared x. f3 of x is secant squared x. And f4 of x is tangent squared x. They claim that's linearly independent on an interval from negative pi halves to pi halves. Now, why that interval? Well, I'm sorry, cosine x, sine squared x, is defined everywhere. Sine squared x is defined everywhere. But secant and tangent are only defined between minus pi halves and pi halves, continuous there. You can go to the next increments and they can be defined too, but they're not defined at pi halves, negative pi halves, or positive pi halves. So we'll have to keep all functions in between there. Well, now this should be, from your trig, something you can think of pretty simply. And let's go to the screen sharing, the whiteboard, if we have time. We got 6 minutes. Where is that? There it is. Okay, now I've got the arrow back. I don't know how that happened, but it did. So let's go back to the whiteboard. Okay, and let's clear those drawings out of the way. Okay, now here's what we had: 4 functions. y1 was, no, bottom, okay, I was on the wrong part of the page. f1 of x, oops, let's get out of baby blue, or let's go back to black for now. Okay, f1 of x is equal to, why the second one will not write, cosine squared x. Now, to me, this was sort of obvious. f2 of x, as soon as I saw those squares, I knew we could fill it with something. That's sine squared x. Okay, f3 of x, okay, is secant squared x. And f4 of x is equal to, there it does it again, tangent squared x. Okay. Now when I saw those squares, I immediately thought Pythagorean identities. And sure enough, that's true. Let's see, when you add these two together, what do you get? Sine squared x plus cosine squared x is equal to 1. Okay? Now, there's another Pythagorean identity that goes something like this. Tangent squared x plus 1 is equal to secant squared x. Okay, so therefore I could also say that tangent squared x let me do it this way. Secant squared x minus tangent squared x, in other words, subtract tangent from both sides, that's equal to 1. And therefore, I could say that, there it is, sine squared x, it's not writing everything I'm trying and then writes where I don't, plus cosine squared x, that's equal to 1, and if I reverse the subtraction here, that would make this negative 1, wouldn't it? So if I then say plus tangents. How did that? Oh, I know how it happened. I'm trying to write too fast, talking too slow, or something like this. I can't get the pen up here where it needs to go. Come on, pen. There you go. Now I can't get the eraser to work. Okay. That's supposed to be a plus, and this is supposed to be tan squared x minus secant squared x because if secant squared minus tangent squared is 1, tangent squared minus secant squared is minus 1, and this sine squared plus cosine is plus 1, this is minus 1, that's equal to 0. Guess what? This set is not linearly dependent. It is linearly dependent, not independent. Why? Because there's some set of coefficients, not all 0, for instance 1, 1, 1, and minus 1, for those 4 functions that give you a solution equal to 0. And I think that's pretty much what they say in the book. If I can find it, it's over on the next page. Yes, if except the secant squared was F3, so it's 1, 1, minus 1, 1. Okay, we used here, so we have done it. And now we're within 1 minute, so I think we're going to have to stop there. I know y'all are very disappointed at that. Let me erase my scribble in the book and come up with a new. We'll start next time, page 124, near the top of the page there, right at the end of that problem. Okay, let me give you some homework exercises. Okay, this is a long first section. Okay, I think you can do any of the either 1 or 3. They're both answers in the back of the book. If they're back there, try to do those. I would say 5 or 7 if they're in the back. 9 if it's in the back. I think 11 if it's in the back. Oh, that may be enough for now. Okay, if some of those get beyond what you think we've done, hold off, we'll pick up the rest of them. I know you can do at least 1 or 3. I think you can do some of the others. Okay, and we'll pick up and go from there. All right, any questions on what we've covered so far? All right, one more assignment, and that's have a good but safe 4th of July weekend. Okay, enjoy. Good news, we won't be missing any of this class. The bad news is if you're in a Monday, Wednesday class, since they took Monday as a holiday, you're going to miss that class. I don't know if any of you are in those. All right. Any last thoughts, parting shots, questions? If not, yeah, okay, thank you. Let me go on and get out of here then. I'll stop the sharing. I'll end the recording, end the Zoom. Any last questions? Oh wait, we can't end the Zoom, for I'd lose you then. Okay, so let's not do that. Okay, y'all can leave if you want to. Okay, Melissa's going to choose to stay. Y'all are welcome to stay and watch too if you'd like. I'm going to end this and that. Melissa, can you see? Yeah, you can still hear me, can't you? Okay, let me see if I can get this in front. That's not what I want, so I'm going to end that too. And now I'm going back to YouTube. Okay, I'll set this out of the way for a moment and go to YouTube. You probably can't see what I'm doing, can you? Okay, I'll put it on in just a minute. Let me sign in here. No reason you have to watch me do this. Okay. Nope. I can't type now. I don't know why. Okay, I'll try to get you back in the picture here. Okay, we still got everybody. Welcome. I'm glad y'all are welcome to be. Let me see if I can get screen. Let me see if that's it. No. Yes, it is. Okay. All right. Now I got to get Ricky out of the way. Ricky, you're always in the way here, you know. Okay, here we go. So let's go to my channel. All right. This is the one I want to edit. It says 4 hours and 21 minutes and 53 seconds. Okay. So I click on that. Is that right? Okay. There it is. Now, how do I, what did you call it? Okay. Okay. Are you hearing me talk? Okay. Wait, I can't hear you if I don't have this on. I don't know why I got this. Okay. What do I need to go to? Okay, wait. Let me go back and get this to shut up. I don't know why it started talking then. I don't usually have that happen. Let me just click once and see if that works. Okay. I think that's better. I hope so. No. Pause it. Where is that? Right. It's what? Up here, the 3 lines? Oh, at the bottom. Right here? Thank you. Okay. Now what? I can put. Do what do you say? Okay. Oh, those 3 dots. Okay, got it. I hit them once. Okay. Do you see what happened? Is that what you want? Okay. Well. Okay, I went there before. Okay. That's where I thought I would need to go. And last time I went to editor, I don't know if that's where I should have gone. Yes, okay, I see it. Okay. Private. Okay. And that is still there, but no one else can see it. Is that right? Okay, am I done now? Okay. Okay, so I hit done now? Okay. Thank you. Now, because I've already, right. Right. Okay. So what I just realized is I forgot to turn off the recording for our class. So let me go back and do that. Yeah. Let me do that real quickly. Okay. Do what? Click zoom. Save. Circled it. Oh, over here there. Yeah. Okay. I see it. Okay. Okay. Now what do I do? Get out. Okay. I'll sign out for now. I'll come back later and fiddle with the rest of it. Okay. Let me okay. All right, thank you. I'll end the recording, end the Zoom now. Is that right? Okay. So let me see if I can get to it anymore. There we go, I think. Well, it says return the meeting. I guess I have to return the meeting to end the meeting. So I'll stop the sharing, and now I'll end the meeting. All right. Thank you so much. All right. You do too. Thank you. Bye-bye.